Hi, I'm Daniel Delafuente.
I'm Kalia Lafferty.
I'm Thomas Mendez.
Our coach is Dr. Adam Rumpf. We are all students of Florida Polytechnic University. And for SCUDEM competition 2025, we are team 1048, and we have chosen problem A. It is raining space dust. To begin, we need to talk about what is cosmic dust. So first, in space, asteroid collisions and comet disintegration causes tiny particles to fly through our solar system. And then as they get near Earth, the Poynton-Robertson drag force, which is when sunlight makes the particles lose angular momentum and spiral towards the Earth, makes them fall towards our atmosphere. And when this happens, as they're entering our atmosphere, they can fragment, which is when they break apart into tiny particles. And depending on their size, they can either burn up in the atmosphere or land on our planet. So for our model, we represented it with a system of ODEs that models the height of the meteor, the velocity of the meteor, and the mass of the meteor as functions of time. We chose these variables because they're the most prevalent properties, and simplifying them as a simple function would result in great inaccuracy. This system of the ODEs are too complicated to be solved analytically, so we used a computer to solve them numerically. Most of the constants in the models are with respect to the variable, to the material, so the model can be generalized for any cosmic particle. Some of our models include the mass, height, and velocity of the particle at time t, the cross-sectional surface area, the density of the air, which is a exponential decay function in terms of height, a heat transfer factor lambda, and a drag coefficient of 0.5, which is typical for spheres, and a latent heat of the material. Some of the assumptions of our models is that the particles will not fragment. Implementing fragmentation was too difficult for the scope of this project, so one of the assumptions we made is that we will not include fragmentation. We also assume that they're dense and non-porous, which means they're solid throughout. We also assume that the density of the particle is constant throughout, so there's no parts with more mass than the other. It's all the same density. We also assume the particle to be a perfect sphere. This is valid because they're pretty small when they enter our atmosphere. Particle will fall with no horizontal movement, so it will fall perfectly vertical into our atmosphere. And our last assumption is that the height, velocity, and the mass of the meteor will change in time. To derive the model, for the height ODE, I simply just made it the velocity function because the derivative of height is velocity. And I chose the convention that the downwards y direction would be positive. For the mass ODE, I used some concepts of power transfer of the meteor from the air and cross-sectional areas to get the equation you see on the right. For the velocity ODE, I used momentum transfer principles, again from the air to the meteor, along with drag force equations to get a final equation for the change in velocity with respect to time, as you see. Again, if we assume height, mass, or velocity is a simple function, that would greatly simplify the model and to the point of it not being realistic enough, and we will get inaccurate data, which is why we need them as a system of ODEs. Combining all these, we get our model for cosmic particle ablation.
So this is an example simulation with a particle that has an initial mass of 100 kilograms, an initial height of 100 kilometers, and an initial velocity of 11 kilometers per second. This basically shows that a particle with an initial mass of 100 kilograms and initial velocity of 11 kilometers per second will burn out. And now looking at the second graph, which shows all the mass and velocities with the final mass, we can see that more mass and less velocity typically leads to more final mass. This means that with less velocity and more initial mass, they are less likely to burn up. And that being said, more velocity will mean that the particle is more likely to burn up. Now, looking at the data versus our predictions, they show similar behaviors. However, theirs drops off more quickly. This can be due to our simplifying assumptions as well as I-type meteoroid particles, which are particles that are dominated by iron oxide and metals, are typically more porous, and they're especially more porous compared to other particles. So that could be the reason for a quick drop off, meaning they burn off a lot quickly. Now looking at the readjusted bins, originally the bins were readjusted to match the data. However, ours captures a lot more variance within the mass. This could also again be because we assume that it is a perfect sphere. Thus, when it is simulated to burn out, it doesn't burn out as quickly as, say, something that is more porous. Now looking at a different type of particle, the S-types, this also shows similar behaviors. However, ours drops off a lot quicker. This could also be due to our simplifying assumptions. However, as you may notice, the S-type mass is dropping off a lot quicker than the I-type. That is because they are less porous.
And finally, to answer some of the questions asked in the prompt, how can particles found on Earth's surface be used to better understand the phenomena? Well, given our model allows us to get some indication of the initial mass and velocity of the particle when it's entering from the final by working through the model in reverse. And given the particles found on Earth and comparing them to particles found in space, collected data, we can see how the ablation process changes these particles as they enter the Earth's atmosphere. And by better understanding how ablation affects these particles, we can more accurately predict how they enter. Here, what happens to particles as they enter the atmosphere? These are two graphs. Both are from a Monte Carlo simulation. The left graph is final mass versus initial mass, and the right graph is a linearized version by taking the log base 10 of both final mass and initial mass. Looking at this graph, we can see that small particles have a high surface area to mass ratio, so they heat up faster, reaching melting temperature sooner, and lose a larger fraction of their mass, while larger particles have a lower surface area to mass ratio, meaning that they cool less efficiently, but their interiors are more shielded, meaning they ablate less proportionally, even though they might lose more absolute mass. So smaller micrometeorites experience more severe ablation and lose a larger percentage of their initial mass. That's what the graph shows us. Finally, is it possible to use an estimate of the distribution of the particles of cosmic dust within a given strata of the Earth's surface from a certain time period and work backwards to find a distribution of the particles that entered the Earth's atmosphere at that time? Yes, it is possible. If you, for each individual particle, work backwards from our model and take a summation of all that, you can use that to find the distribution of the particles that enter Earth's atmosphere at the time. However, there may be some error as our model does not account for fragmentation. And that is all. Thank you for allowing us to participate in this competition, and have a great rest of your day.